So my name's Chloe Canning.
My name's Leah.
And first we'd like to welcome you to our presentation and acknowledge that we're on Treaty 6 territory, homeland of the Métis, and that our samples were taken from Treaty 11 territories. So our project started with the first year research experience, and in that we were given a set of samples from the Yellowknife area, and we were able to do kind of whatever we wanted with them, with the guidance of our teacher there. And so we chose a set of tree cores to work with, and this is what we did with them.
So Yellowknife is located in northern Canada and is the capital of the Northwest Territories. This here is the city of Yellowknife. The giant mine is located just to the north, highlighted in red on the map. The giant mine originally brought economic development and growth when it opened in 1948, but then it started releasing arsenic into the environment from its mining activities. Soon it was realized what the social and environmental impacts of the mine were. There has been many health issues related to the mine. The government only gave $1,000 to a family who lost a child who ate snow near the mine. There's a poster for arsenic testing that is taken from Yellowknife, and it is something that we don't see here. Each green pin on that map is a species that we could have chose, but we chose white birch and jack pine because they were there before the mine had opened. They are located on the northwest corner of the mine's borders, which is also downwind of the mine.
So as she said, the two species we chose were white birch, which is a deciduous tree, and jack pine, which is coniferous. So just to kind of look at how our samples were collected and how we prepared them, this is a photo here of Zach from the Mad Lab, and he's coring the tree and getting our tree cores. This is what the actual core looks like before it's prepared and ready to look at. And basically what we do is we glue down those cores and we sand them down. And then after sanding, we're able to see the rings through a microscope. And so we count from the bark to the pith, so kind of right there. And that gives us the relative age of the trees. And we're actually able to date them quite accurately.
So we used the X-ray fluorescence method, which has a small window, as you can see on the right-hand side there. That is about the size of a quarter. A beam of light is sent up through that window, which excites the electrons. The electrons bounce off certain energy levels, depending on what they are. The element leaves a photon trace that the detectors pick up and are analyzed for identification.
So this here is a timeline of the giant mine, kind of looking at important and key dates that happened throughout the time, I guess. And some things to highlight are in 1958. That's the highest level of production that the mine was at. So they were producing about 1,000 tons of ore per day. And then in 1962, they found that they're gathering quite a bit of arsenic trioxide, and the best way to deal with that was to send it underground in the permafrost. Then in 1974, they started open pit mining. So before, the arsenic was and everything else was relatively contained inside the mine, but when they moved to open pit mining, everything was exposed to the environment. And then in 1999, after the mine went bankrupt a couple times through a couple different companies, the government of Canada finally bought it and basically moved forward with remediation. And this is also around the time when they realized that due to climate change, the permafrost is no longer frozen all year round, so they decided that the new best way would be to mechanically freeze it throughout the year.
This is our raw data that we collected from their X-ray fluorescence method. It gave us the relative concentrations of arsenic in each sample. These are the graphs that we got from the raw data.
So just kind of going through line by line with the kind of comparing our timeline to the graphs we got from our first set of data. you can see that the two trees, white birch responds more to the arsenic and kind of changes it a lot more, while jack pine is not quite, it doesn't change quite as much. But the thing that we found really interesting here was this huge anomaly in the white birch. So it basically goes from very little arsenic to a whole bunch rather quickly. So we kind of switched over to looking at, well, why is that anomaly there? Some hypothesis for why this is there is perhaps it's because the tailings ponds from the mine, which were downwind of our samples, those could have dried up. Therefore, any arsenic inside those tailing ponds would have also dried up, and then through the wind would have been sent straight to our samples and into the surrounding environment. And then also it could possibly be because that arsenic was always there, but because that tree grew really well that year, it could have taken up a lot more because it's different from the jack pine. Jack pine didn't show that.
So after using the X-ray fluorescence method on the smaller scale, we got the opportunity to go to the Canadian light source, also known as the CLS. The CLS is the only synchrotron in Canada, and people come from everywhere to use it. The CLS is a much larger version of the XRF and takes much less time to get similar data. We used the IDEAS beamline, which allowed us to look at the fourth row elements on the periodic table, which is where arsenic is. These are the spot graphs from our two trees. It is the relative counts at 3 points along the tree core. This is the scan across the core of the jack pine, stopping every 1 millimeter. As you can see, there isn't much difference along the jack pine, but with the white birch, you can see that there is much more movement. The anomaly is still present, as you can see with the white birch on the bark side of the core, which could again be something to do with the plumbing of the trees, as Chloe said earlier.
So this is our spot graph zoomed in on the energy level that arsenic is found at. So basically anything below 50 counts is, you don't really have anything there. It's just other elements being counted, not really, you don't really have anything. But anything, so that's kind of considered the safe level of arsenic. But then anything above that is considered to be an unsafe level, because really any arsenic is an unsafe level of arsenic. And as you can see, with our anomaly especially, we have a big spike in the number of photons counted for arsenic. So we have confirmed that arsenic is present in our samples. And that's a huge cause for concern for the people that live there and work there and everything. So some things to kind of consider are that from our first set of data, from the small XRF, even though the relative concentrations aren't necessarily the most accurate, they still confirm that there is arsenic in there and that the levels are much higher than acceptable drinking water levels and uncontaminated soil levels. So, as we said before, any level of arsenic is not a safe level, so this is a huge cause for concern. And one possible explanation for this that's not related to the mine is that arsenic is naturally occurring and can be found in the bedrock in the area. So it's possible through erosion that the arsenic could have been in the groundwater table and then gotten into the soil and then is taken up by our trees. But further testing would need to be done to know if that's actually the case, and also speciation of the arsenic, because the byproduct of gold mining arsenic is much different from the naturally occurring arsenic. And one is much more toxic and deadly than the other. So kind of a control tree in the area, but not affected by the mine is kind of the next step for us. And kind of looking at the soil samples from around that tree to know how much is in the soil, and then also looking to see how far the arsenic extends. Our samples were taken relatively close to the mine, but does it go 20 kilometers away, 30 kilometers, 40? So that's kind of the next step for us.
So why does all of this matter? Here in Saskatoon, we don't really know where our groceries are coming from. But many of the people who are living in Yellowknife are hunting, gathering, and growing their own food. So what happens where in a place where you are living off the land, where everything is toxic? The social implications of this environmental mess is making a huge impact on these people's lives, and we believe that more people should know their story. With basic research and increasing awareness of this issue, we would have the opportunity to identify the actual reach this arsenic has, or the arsenic pollution has in this community, as well as other mining communities around the world.
So just a quick thank you to Colin, Brooke, Zach, and Tracy. Without them, we probably wouldn't have been able to do this, since it is our first year of university and first research experience, and so they really helped us get through and figure out what we were doing. And then thank you to everyone for listening, and hope you all learned something interesting, and if there are any questions, we're ready to take them.
Thank you.